Hello everyone, today we're going to go over section 10.3, which is on the ellipse. So we have three objectives. One, we want to analyze ellipse with centers at the origin. Two, analyze ellipses with center at h, k. And three, solve applied problems involving ellipses. So the plural version of ellipse is ellipses. I think I accidentally used the singular version ellipse with that first objective, but it is ellipses versus ellipse. So, all right, the definition of the ellipse is that an ellipse is the collection of all points in a plane, the sum of whose distances from two fixed points called the foci is a constant. So just a little bit of a definition of an ellipse we see here in our image that we have what looks like an oval. So an ellipse is a mathematical term for an oval, essentially. But a mathematically calculated oval. And so we see here that we have this oval-like shape. We have labeled a minor axis and a major axis. We have these points V1, V2, these are called our vertices, and F1 and F2 being our foci. This center point where our minor axis and our major axis crosses as our center, and P is just a point that we have plotted on our ellipse. It's drawn in this way with what looks like two thumbtacks, a string, and a pencil, because the way that you can draw a perfect ellipse is that if you put in two tacks at your foci, you attach a string of a certain length, take a pencil, you can perfectly draw your ellipses that way. So, all right, in our image, F1 and F2 are going to be our foci. The line containing the foci is then called the major axis. So our major axis kind of looks like our x-axis in this case. The midpoint of the line segment joining the foci is the center of the ellipse. The line through the center and perpendicular to the major axis is the minor axis. The 2 points of intersection of the ellipse and the major axis are called the vertices, VI and V2 of the ellipse. So we see those values V1 and V2. The distance from one vertex to the other is called the length of the major axis. So the length of the major axis in this case would end up being this length here, so from one vertex to the other. Then we have that the ellipse is symmetric with respect to the major axis, minor axis, and its center. So we have that it is symmetric, both length and width size there. So all right, objective one. Done with our little intro, now we're going to analyze ellipses at the origin. So our first theorem, we have the equation of an ellipse where its center is at 0, 0, and its major axis is going to be along the x-axis. So the equation of the ellipse with center at 0, 0, foci at negative c, 0, and c, 0, and vertices at negative a, 0, and a, 0, is going to be x squared divided by a squared plus y squared divided by b squared is equal to 1, where a is greater than b, which is greater than 0, and b squared is equal to a squared minus c squared. The major axis is the x-axis, as we see in our image here. So our image now off to the right is our ellipse centered at 0, 0 along the x-axis. So we see here that our value of b is used. Our value of b would then be the y-intercepts that we have there. Our values of a would be our x-intercepts. And then c would be our length between the center and the foci. We can use intercepts to easily and effectively graph an ellipse. So let's do an example. So we want to find an equation of the ellipse with a center at the origin, one focus at 2, 0, and a vertex at negative 3, 0. Then we're going to graph our equation. So let's first write about it, and then we'll leave graphing for the end here. So we can determine that we already know the ellipse is at the origin, which is at 0, 0. And since the given focus and vertex focus and vertex lie on the x-axis. We know that it lies on the x-axis because the x values are the ones that actually have values and are not 0. So that's how we know that it's on the x-axis. Then the major axis lies on the x-axis. All right, so all that to say, we have determined that we now know the major axis is on the x-axis. Then the distance from the center to our given focus is C. And remember, C is the distance between your center and just one focus. So it's not the distance between your two foci, but just center to focus is going to be C is equal to 2. Since we're given that one focus is at 2, 0, we know our center is at 0, 0. So C is equal to 2. And the distance from center to the given vertex is A equal to 3. Since we have one vertex at -3, 0. So our distance is A equals 3. We could write -3 if we like. It doesn't really matter because the distance is in both directions in this case. So just the core value of the distance would be 3. Then, so we can say then we get that B squared is equal to A squared minus C squared. So we want to find B. So we know that A is 3, A squared, so 3 squared would end up being 9, and 2 squared would end up being 4. So we get 9 minus 4, which is then equal to 5. So B squared is equal to 5. So now we can determine the equation of our ellipse since we do want to find the equation of the ellipse. All we were really looking for in this case was B squared, since we already or could easily find what A squared was going to be. So we get it's A squared plus Y squared over 5, because remember it's over B squared. We know that B squared is 5. And it's always set equal to 1. And there's the equation of our ellipse. So now we want to actually graph this equation. So let's graph the things that we already know. We know that one focus is going to be at 2, 0. We know the center is at 0, 0. So here's our center. Our first focus is at 2, 0. So we'll name this F1. And actually, let's go ahead and mark this in red. And our vertex is at -3, 0. And we'll label this V2. Actually, we'll reverse this. We'll say this is V1 and this is going to be F2. So we have everything marked. Now our focus has to be the same distance away from the center for both sides. So since our first focus, or F2, which we stated was 2 equals 0, this will be F2, and this is V2, we want to go ahead and graph these equations now. So we want to graph our other focus, and since focus 2 is going to be at 2, 0, we now go in the opposite direction to get -2, 0. So this will be our focus 1. Then to find our second vertex, same way. We know that the distance the distance in this case A for the given vertex was 3 in the left direction or 3 in the negative direction. Now it has to be 3 in the positive direction from the center. So that means that our second vertex, V2, is at 3, 0. Then, all right, last thing we want to do is we want to find those y-intercepts. Our y-intercepts are going to be positive and negative b. So we'll put this here. Y-intercepts are going to be plus or minus b, 0 plus or minus b. So we get 0, negative square root of 5, and 0, positive square root of 5. Where our square root of 5 is actually just slightly more than 2, so we can go ahead and plot that. So it's going to be right about here. This is our square root 5, 0, and right about here is our 0. Whoops, wrote that wrong. 0 square root 5 and 0 negative square root 5. So we've drawn all of our points. Now what we need to do is just connect all of our blue points in this case, except for the center. So we want to connect our y-intercepts, and we want to connect our vertices. So remember our vertices, this is a, 0. This is negative a, 0. This is 0, b, and 0, negative b. So let's go ahead and connect these points. Let's move this out of the way. Good enough. Connect this point down here and connect our last point. So if that were even, that would be correct. That would be our graphed equation of our ellipse in this case. So, all right. If the major axis lies on the y-axis, the foci are then going to be 0, negative c, and 0, positive c, and our definition will then become our next theorem of the equation of an ellipse where the center is still at 0, 0, but the major axis is now on the y-axis. So an equation of the ellipse with a center at 0, 0, foci at 0, negative c, and 0, c, and vertices at 0, negative a, and 0, a, is now going to be x squared over b squared plus y squared over a squared is equal to 1, where now a is greater than b, which is still greater than 0, and b squared is equal to a squared minus c squared, where now the major axis is the y-axis. So we see our image definitely looks different. Our foci and our vertices are now going to be located on the y-axis as opposed to the x-axis. But as far as our actual equation goes, the equations look very similar. The thing to notice is that equation 2 has the larger number, which is usually a squared. Well, sorry, not usually, is always a squared because a is greater than b, which is positive. So we see in equation 2, we had x squared over a squared plus y squared over b squared was equal to 1. Now, when our major axis lies on the y-axis, it's going to be x squared over b squared plus y squared over a squared is equal to 1. So whichever is the larger value under either the x term or the y term, so whether it's under x squared or y squared, tells you what the major axis is going to be. So if you have something like x squared over 9 plus y squared over 16 is equal to 1, 16 is the greater value, you would then have an equation of an ellipse where its major axis was on the y-axis. So that's the key point to look for there. Then we see equation 3 has the larger number a squared in the denominator of the y squared term, so the major axis corresponds to the y-axis, where if it were under the x term, it would be the x-axis. For the remainder of this section, you're going to hear analyze the equation in given problems. This just means that we want to find the center, we want to find the foci, the vertices, and then we're going to graph. So the 4 things that we have to do there. So for equation 2, we're going to analyze the equation 9x squared plus y squared is equal to 9. So the first things first, we want to put this equation in its proper form. This means that we want to have denominators and we don't want any coefficients. If we divide each term by 9 in this case, this will end up giving us x squared over 1 plus y squared over 9 is equal to 1. So now we have our equation in proper form. So then we get, since the larger denominator is in the y term, we have the center at 0, 0, and the major axis is on the y-axis. All right, so we know our center and we now know where our major axis lies. Now we want to solve for our a squareds, our b squareds, and our c squareds. So then a being our larger value, a squared is going to be 9. B squared is 1. So c squared, which if we rewrite this equation here, c squared is going to be a squared minus b squared. So we get c squared is equal to a squared minus b squared, where this is then equal to 9 minus 1, which is equal to 8. So we've now determined what a squared, b squared, and c squared is going to be. So we get that the vertices are plus or minus, 0, comma, plus or minus a will be 0 plus or minus 3. The foci are going to be 0, comma, positive negative c. That would give us 0 plus or minus, and we have the square root of 8 in this case. The square root of 8 can be separated into the square root of 4 times 2, which the square root of 4 is 2, so this actually just becomes 2 times the square root of 2. Then lastly, the x-intercepts there we go, are plus or minus b comma 0, which gives us plus or minus 1 comma 0. So with our plus or minus signs, this means that we're really including both. We have to make a point for the vertices at 0, comma 3 and 0, comma negative 3. Our foci are going to be at 0, 2 times square root of 2, and 0 and negative 2 times square root of 2. And the x-intercepts are going to be at 1, 0, and negative 1, 0. So let's go ahead and plot all those points. Our center is at 0, 0. It's at our origin. Our vertices are going to be at 0, 3, and 0, negative 3. So here's V1, V2. Our foci are going to be at 0, 2, square root of 2, and negative 2, square root of 2. Those values are going to come out to a little bit more than 2, but not 3. So probably about right here. So this will be F1 and F2. So we have our center, our vertices, our foci, and now we just need our x-intercepts, which we know are at 1, 0, and negative 1, 0. And now we have everything that we need to go ahead and graph our ellipse. So we're connecting our x-intercepts with our vertices. Remember, our foci would be that if we were drawing this out, our foci would be where we would put our tacks to hold that piece of string that we're then using to draw around. So the foci you do not connect values to. They're just going to be in the middle. So the things that we were looking for when we want to analyze our equation is, remember that we want to find the center, the foci, the vertices, and then graph. So we have the center at 0, 0, the vertices, and the foci. So those are the things that we were looking for in addition to our graph. So moving on, a circle can be considered a special kind of ellipse if we let A equal to B. This indicates that the closer the foci are to each other, the more it will look like a circle. So the farther away they are, the more oblong your ellipse is going to look, or more of a longer oval your ellipse is going to look. But the closer they are together, the more it will end up looking like a circle.